The Center for Educational Media and the College of Education at Middle Tennessee State University are proud to offer professional development to K-12 educators in Tennessee through our online video library. These videos are aligned with standards set by the Tennessee Department of Education. For more professional development videos, check out our website at cem.mtsu.edu.
So now, my friend, Dr. Lisa Green, is going to give us a presentation on statistics and probability. I want to make sure I say it correctly. And I'm going to give you a little prelude. You know, everything comes down to probabilities, correct? That's the way I see life. Everything comes down to probabilities. You get in your car, what's the probability of you arriving at your destination, right? So this is really vital stuff. I appreciate Lisa being here. I'm going to turn it over to Lisa. Thank you.
Okay, so what I'm going to do today is take you through the reasoning that we use as statisticians when we're looking at data and we're trying to answer questions. This is really loud. Okay, so I'm going to start with talking about data types and what you would do with the different types of data for descriptive statistics. And then there are two parts of statistics. There's describing the data set that you have, and then there's inferential statistics, which is using what you learned from the data set to infer something about the population. And so we'll talk about how that connection is made, and then we'll do an example for inferential statistics that I actually have a handout, and I'll pass that out at the appropriate time. So I love this data set. This data set is 74,000 beer recipes. Each beer recipe is named, has a URL, which means that you can go to the recipe if you decide that you want to make that beer. And then it's got the style and various other things. There are 23 variables in this data set. We're not going to look at all 23 variables because this is an hour-long presentation and that would be insane. So the ones that we're going to look at are style, alcohol by volume, color, and brew method. Okay? So the first thing that we want to look at is what type of data do we have? How are our variables reported to us? So let's look at the different variables that we have, and let's say which ones are quantitative and which ones are qualitative. So statisticians, we're all schizophrenic. We have two names for pretty much everything. And so for qualitative, you can also call that categorical variable, and for quantitative, you can call that numerical variables. So of these, which ones do you think are quantitative?
ABV?
So ABV, that would be a percent of alcohol, so it's a number. Anything else? We'll talk about color. Okay, what about qualitative?
Style.
Color.
Method.
And
Blue.
And color and brew method, okay? So let's talk about color. We know that if we were talking about cars, for example, color would be a qualitative or categorical variable. But in this case, beer is measured with a particular color scale that is actually measurable because they take a particular wavelength of light and push it through a particular amount of beer and then measure how much light came out the other side, and that's actually a number that can be known. And therefore, color in this case, not always, but in this case, is numerical. Okay?
What does EBC stand for? Beer color? Sorry.
The standard reference method is one way of measuring color, and EBC is another method of measuring color, and I don't remember what it
That's
stands
what Google's for. It's fine.
But this is kind of my point, is that as a statistician, I'm not going to know everything about the data that I'm looking at. And therefore, it's really important for me to be able to have an expert to refer to. And I can go to my fermentation expert and say, what is this? How is it measured? What are the units? That kind of thing. So, once we know what data we have, then we have to ask, what do we want to know? And actually, I'm doing this backwards, because usually you would start with what do you want to know, and then you would go gather data, right? So statistical questions are questions that you can ask about data, what's going on. So here are some example questions. What is a typical ABV? So typical kind of depends on the data whether I would report a mean or a median, but at least I can head into a statistical answer to that question. How much variation is there in ABV? That is a question about standard deviation, right? Or if I decided to measure variation in a different way, I could do that. Do darker beers have a higher ABV? Here I am comparing two different variables, the color and the alcohol by volume, right? And then which style of beer is most popular in Tennessee? That's got a little star by it, because I can't answer that with this data set, right? But it is a statistical question. And so there is somewhere a data set that could address that question. Possibly it's an imaginary data set that somebody would have to do work to collect, but I could answer that question with data. So, are there other statistical questions that you can think of? Calories. This particular data set doesn't have calorie information, but we could certainly imagine a data set that did, and therefore we could report something about average calories or variation in calories or that sort of thing, right? Right? You could, for example, talk about whether the color of the beer affects the calories, right? And that would be a two-dimensional, two-variable question, right? Let's talk about questions that are not statistical. Not every question can be answered with data, right? What's your favorite beer is not a statistical question. Which beer tastes better with this kind of cheese? Not statistical, right? Who developed the first recipe? There is an answer for that. I don't know what it is, and I can't get that from this data set. Okay? So, how about other non-statistical questions?
What's the best kind of beer?
What's the best kind of beer? How do we measure what's best, right?
Is European beer better than an American beer?
Is European beer better than American beer? I could actually turn that into a statistical question. I can turn a lot of these non-statistical questions into statistical questions by changing the way they're phrased. So is European better than American? I would have to collect data on what people prefer, right? And so I would have to have this measure of what is a good beer.
But then
right?
that could be because of cost.
Right. So there are a lot of different ways that you can address these questions. What is John's favorite beer is not statistical, but what is the favorite beer on the MTSU campus? That is a statistical question. Does that make sense? So once I take a question about one person and make it a question about a population, that becomes a statistical question. Okay? Okay, so what kind of data you have controls how you're going to present that data. So I've kind of looked at this in 4 categories. You've got categorical versus numerical, and you've got single versus multiple variables, okay? So let's start with, we've got a single categorical variable. How are we going to present that, right? Right now, we're just summarizing a data set. How are we going to present that? So brew method is a single categorical variable. It has 4 categories. One thing that I can do is just give you the summary, right? 50,000 of these recipes are all grain, and 12,000 are BIAB, which I looked up last night, and now I don't remember what it is. But anyway, and 8,000 are extract, et cetera. I could turn those into percentages, right? And then once I have percentages, I can either make a bar chart or a pie chart or something like that, right? The purpose of the descriptive statistics is to summarize the data set, right? Yeah.
Brew in a bag.
Yeah, it's
Brew in a bag.
It's all grain beer brewing is a new method originating in
So-
Australia. I've already learned more.
And it seems to be fairly popular. It's like the second most popular brew method, so, you know. The styles is a categorical variable, but it has way too many categories for me to summarize with a bar chart or a pie chart. So I can get around that by combining categories. That's why I've got other, right? So this particular chart is allowing me to summarize which ones are the most common styles, right? And according to this chart, American IPA and American Pale Ale are the 2 most common beer recipes. Notice that I'm saying they're the most common beer recipes, not the most common beers, right? Because I don't know anything about the consumption of these beers. I know about the recipes of these beers, right? Okay, now if I have more than one descriptive categorical statistics, then I can look at a table of, here I just took the 3 most popular styles and looked at the brew method for each of those styles. Maybe different styles have different brew methods. You know, maybe that would be an interesting thing to find out. The problem with this chart is that it's hard to see what's going on because there's such a size difference between the different styles. So if I change that chart to be percentages instead of counts, notice that I did put the ends, because once you change to percentage, you lose the count information. So putting it there allows me to retain that. Now I can look at this and say, you know what, those proportions look pretty similar across the different styles. It doesn't really look like the different styles have different brew techniques at all. That's kind of an interesting result to me. Once you have numerical statistics, you can do more with them. Categorical statistics, you're really just looking at percentages, like what's the most common, that kind of thing. But with numerical statistics, there's more information that you can get. So this is a histogram. A histogram has bars where the height of the bar is the count of the number of values that were between this number and that number. So this bar ends at 5 and 10. So the number of beer recipes with an alcohol by value between 5 and 10 is somewhere around 60,000, right? So that's a graph. And then I've got the various numbers that I can report: mean, median, standard deviation. Are we all clear on what the difference is between mean and median and standard deviation? Okay. So are there other graphs that I could use for a numerical data set? Like, for example,
Do pie graph. You could do a box and whisker plot, you
A
could.
box and whisker, I can't pronounce it, plot would be a great idea here. Now, box and whisker plot has a line in the middle for the median, 2 lines on either side for the first and third quartiles. That's the 25th percent and the 75th percent value. And then the ends are usually the minimum and the maximum, but there might be stars or something for outliers, right? So if I did that here, I would get a box plot that had a lot of, the box would be here, and then the whisker would go on like that, right? It's a weird shape for a data set. Let's talk about why we're getting that shape. What's with it going all the way to 50?
Now you're talking grain alcohol. Yeah.
Yeah, I mean, alcohol by volume of 50%, that's 100 proof. For beer?
College kid in a dorm with the recipe.
It makes me think that somebody misplaced a decimal point. Because we know that 5% is very common. It would only take changing where a decimal place is to make that 5% into a 50%, right? So I'm looking at this and I'm thinking, that doesn't make sense, right? So if I change it to, here I'm eliminating any beer that has an alcohol by volume greater than 20%, because 20% seems kind of generous to me, right? So then I get a much more interesting graph. There's a lot more information in here because I didn't have to zoom out so far, right? And so I can talk about the shape and everything like that, right? And that decision to change it from looking at all of them to looking at all of them before 20 only eliminated 54 of my beer recipes. I really do think that those are likely to have been typos. Now, as a statistician, I don't get to make that decision. It is my responsibility to bring that to somebody and say, I'm looking at these values and they don't look right to me, and let them make the decision that those are typos, right? But I can show them the 2 graphs and let them make that decision. So, there's the original values and the new values. If you look at the mean and median and standard deviation, the mean and median didn't change. I would expect the mean to change. Why is it not changing?
Took away such a small value.
Right. There are 74,000 numbers in this data set. And if I'm only taking away 50 of them, I'm not going to change the value of the mean all that much. And the median even less. Why did the standard deviation change?
Because you got rid of those crazy outliers.
Right. The standard
more accurate.
deviation measures how spread out a data set is. And if I get rid of the outliers, I am making it less spread out. And so the standard deviation is going to go down. Okay, so should we use the new data set or the old data set? That's not my decision. That is the decision of the person that I'm consulting for. But I can show them the 2 data sets and say, I really think that there's an error here. Okay? Okay, so multiple numerical. Now, I was sitting back there and I noticed you've already seen an example of multiple numerical values. So what graph would you use? Scatter plot, right? X value, Y value, independent, dependent, whatever, okay? So here I'm looking at color and alcohol by volume. I'm kind of trying to address the question of, do darker beers have higher alcohol content, okay? What's up with that shape? That's a weird shape. Any ideas?
Looks like the beer's boiling.
What's happening here at 50? There's a big line there. When you see big lines like that, that means that some of the recipes had rounded values and some of them didn't. So a lot of people are rounding at 50. And you think, that's weird. Why would you round the color? So we take a look at color. What happens on that chart? What's the maximum value?
79.
No, the maximum value here. 40, right? So a color value of 40 means that this is black beer, right? So that says that according to this chart, 40 is a cutoff. But according to my data set, 50 is a cutoff, right? So let's see. Here I cut off at 40, and here I cut off at 50. Cutting off at 40 eliminates 5% of my data set. That seems like a lot to me. Cutting off at 50 eliminates 37 out of 74,000. That's less than 1%, less than 0.1%. It's a really small number. So I'd probably go with the 50, but I'm still curious why this number goes up to 50 when it says in the description of the data set that it is using standard reference method color values, and the standard reference method goes up to 40. So this is another thing where I would have to ask the person that I'm talking to. Moreover, look at the correlation. So Dr. Martin was talking to you about correlation just now. What's a high correlation? What's a low correlation?
High would be close to 1.
Right.
So,
A correlation close to 1 is pretty high. And what does a correlation close to 0 mean?
it's not
A
correlated.
lot of variant.
A correlation close to 0 means that there's no relationship between these two. Now, a correlation of 0.27 means this is very slight relationship. There's a relationship, but it's weak. So you can tell by the picture too. The darker the beer, the higher the alcohol by volume, but only by a little bit, and there are a lot of exceptions to the rule, right? So yes, there's a relationship, but it's really slight. Does that make sense? So again, how do we decide which data set to use? We go ask the person we're consulting with. This is the beautiful thing about being a statistician, is that I'm always learning new things, because I have to understand the data in order to analyze the data. And so I'm learning about genetic expression, and I learned about clouds, and I learned about telescopes, all sorts of different things, because in order to be a statistician, I have to understand what is being measured. Okay? Okay, so let's talk about taking the description of a data set and using it to infer about the population. In order to do that, I need to understand what my population is and what my sample is, and how my sample was obtained. So a population, that would be everything related to the thing that I'm interested in. So I might be interested in the population of all college students in the United States, or I might be interested in the population of all women between the ages of 35 and 50, right? Something like that. And then the sample, that would be a part of the population that ideally is representative. The representative part means that the sample pretty much looks like the population. And the best way to guarantee that you have a representative population, representative sample, is to choose it randomly, because that way you get a little bit of everybody. So if I'm interested in all women between the ages of 35 and 50, then I would do the equivalent of putting all of those names in a big bag and pulling out values. Does that make sense?
Hence the phone calls.
This is why you get phone calls, right? So that brings us back to the beer data set. What would the population be for this beer data set? And do we think that this beer data set is representative of that population?
All beer recipes. Maybe the types of beer.
So the thing about this data set is that it's recipes, right? So it's not talking about beer that is being drunk. It's talking about beer that is being made by hobbyists, right? So the population might be all beer being made by hobbyists, right? Is it likely that our sample is representative of that?
It seems to be, since you got 74,000 different recipes.
I've got a lot of different recipes. Is it reasonable to think that the fact that I have a lot of them means that they look like the population?
Depends on how you got it.
Chances are not. And the reason I say not is that they probably wrote down every recipe they could find, which means that they were not choosing the recipes randomly, they were choosing them, it's called a convenience sample, right? And so if there is one that's popular in, say, California that happens to not be in the data set, it's not being represented, right? So furthermore, it's likely that several people are using the same recipe and other recipes are not really being used by anybody. So I don't have any way in the data set to know that. So I can use this data set as itself, as a data set that is a fairly big data set of beer recipes. But to use it as a representative of a larger population is a little bit iffier. This data set can answer certain questions like, are darker beers likely to be higher in alcohol by volume? But they can't answer other questions like which beer recipe is used most often, because that data is not in the data set, okay? So, because this data set is not a representative sample, we would not make the connection between the data set and the population. But sometimes you get data sets that are representative. This one that I'm about to talk to you about is also not representative of everything that we want it to be representative of. But we can use it to generalize to a different population, a smaller population than the one that we're interested in. Now, this handout is the student handout for an activity that I would use in a class, pretty much the first day of class for a statistics class. And there is a website mtstatpal.com, and if you go to the teacher page, there's a master calendar with key, and you can type in the password, which I'll give you in just a minute, and it has a list of topics that are going to be covered in this class for the entire semester. What's nice about it is that the handout for the activity is there. The teacher's handout, so it has the student answers and also comments on which things you should emphasize, which things you shouldn't emphasize, are there. And a video of somebody doing this lesson is there. So if you decide you want to take a look, you can go to that website. I should also mention the regression on the rebound, because this activity is the ball bouncing activity that you just had data for. So you can watch. That's 4 groups of 4 and 1 group of 5. Okay, so I'd like to have you get into groups of 4 and 5, and so they're dropping balls and recording how high they bounce. So that site, which is mtstatpal.com, is very useful, and the teacher password is INST for instructor, mtstatpal. Okay.
Between their thoughts and their behaviors.
If you both want to do different things, what could you do?
How we reason about other minds in the world.
Peekaboo!
We began addressing some of these questions with infants.
In this study, parents bring their 6-month-olds into the lab.
At the other side of a long table is a hill stage. A red circle guy with googly eyes tries to climb the hill. He sort of goes up the hill and then falls back down. He always fails at it. Then a blue square character, also with googly eyes, comes from the bottom of the hill and bumps him up to the top of the hill so that he's successful. On different trials, the climber tries again to get to the top of the hill, and then a yellow triangle character comes down from the top and bumps him to the bottom of the hill, so prevents him from getting his goal. Babies see this a number of times until they get nice and bored with it. So we stop and basically do a choice measure. Moms are asked to close their eyes. An experimenter who did not see which character was which brings over the 2 characters to the babies and just sees which character the baby touches first.
Which one do you want?
We found that, impressively actually, almost 100% of babies.
We'll talk about what they found later. So this activity usually takes about an hour, but we have 15 minutes, so we're going to go really fast, okay? The first thing that I would ask a student is, why did mom have to close her eyes, and why did the person giving the toys have to not know which was the helper and which was the hinderer? Bias. We're trying to eliminate any source of the baby's making a choice other than the baby's made a choice, right? And usually students bring up, what if the babies like yellow? What if the babies like blue? What if they like squares better than triangles? And this is where you get to talk about how the people doing the study would switch out which toy is the helper and which is the hinderer for each baby, okay? So in the study that we're talking about, they had 10-month-old babies. The one that you were looking at was a 6-month-old baby, but it's the same experiment. So 16 10-month-old babies did this study. Now, if the babies had a preference for the helper toy, what would you expect to see?
The helper.
More helper toys being chosen, right? So the question that we're interested in is, how much more? So if the babies didn't have a preference, we would expect how many?
50-50.
50-50, which is, for 16 babies, that would be 8, right? So if we got more than 8, then we would expect that, we would conclude that the babies had a preference. But the question is 9 enough more than 8? How about 10? How about 11? Like, where's that cutoff between how much more is more, right? That's where the statistics comes in, okay? So what we would do is we'd say, let's pretend that we are babies with no preference. Take one and pass it down, okay? We are babies with no preference on whether we like the helper or the hinderer, okay? If you flip that coin once, that is one baby making a choice. And for the sake of argument, let's say heads means that you chose the helper toy, okay? So you flip the coin one time, that's one baby choosing the helper toy, right? If you flip the coin 16 times, what are you simulating?
The population.
Not the population.
Sample.
The sample. There are 16 babies that we looked at, and so by flipping the coin 16 times, we are making 16 choices. And we're assuming that this baby does not have a preference because the coin will come up heads 50% of the time, right? So go ahead and do that. 16 times, flip the coin, and record whether you got helper or hinder for each of the 16 times. Okay, I want you to count how many heads you got. That's going to be how many babies chose the helper toy, okay? And then tell me how many heads you got.
I got 11.
Okay?
I also got 11. 7. 9.
Who's that?
4. 6.
7.
7.
10.
Is that everybody? I think that's everybody. So this is simulated the experiment under the hypothesis that the babies have no preference, right? Now, ideally, we would do this thousands of times, but that would really take a long time, right? But luckily, we have technology. So this applet is one of many that exist online. Coin toss in Google will get you something like this. So we want the probability of heads to be 0.5, so it's a fair coin. We want there to be 16 tosses of that coin. And if I look at that, then in this particular case, we got 11 heads, and there's a dot here at 11, okay? And this time there were 6 heads, and there's a dot at 6. But the dot at 11 stayed, right? So this app is just basically doing what you just did, right? So if I unclick the animate button, always unclick the animate button, because if you don't, you're going to be here forever. And then I'm going to make it 998 more repetitions because I've already done 2 and I want a total of 1,000. I get this graph. So basically the dots kind of all smushed onto each other because there are 1,000 of them, and so they start looking like lines. Does that shape look familiar?
It's a bell curve.
Okay, bell curve, right?
Same as the beer recipes.
It's amazing how this just keeps coming up. That's why it's called the normal curve, because it's normal. It keeps coming up in all sorts of situations. So this is what we would expect to have happen if the babies had no preference. So 8 is the most likely. You see the line at 8 is highest. But 7 and 9 are pretty common. In fact, so are 6 and 10. So how high would the number choosing the helper toy have to be for you to decide the babies had a preference? 16? So even 15 would not have doubt in your mind? So how many 15s did we get? None, right? How many 14s did we get? Luckily, we can count. there were 3 14, 15, or 16s. So out of 1,000 times, 3 times came up as 14. Now, does that make a 14 rare enough for you to start thinking, yeah, that's not a fair coin? If you flipped a coin 16 times and you got 14 heads, would you start thinking that that coin was not fair?
Yeah.
Guess what? 14 of the 16 babies chose the helper toy.
So they have a preference.
Yeah, so we conclude that the babies had a preference for the helper toy. Does that make sense? Now, why are we concluding that? We're calculating this proportion, which ends up being a probability. It's called a p-value. In fact, on the 3rd page of your handout, it says a p-value is, okay? It's got a little box around it. A p-value is the probability of getting the data that you actually did get if the null model is true. So what's a null model? Null model is the boring model. It's the there's nothing here worth looking at model. In this particular example, it's the babies didn't have a preference model, right? If you're looking at manufacturing, it might be that the new manufacturing isn't any better than the old manufacturing process. Or if you're looking at cars, it may be that there's no difference in miles per gallon between this car and that car. It's the boring hypothesis, okay? So the null model is the boring model. In this case, no preference. So if there is no preference, what would we expect to have happen? There, we've got it, okay? And then based on that, how likely is what we actually saw? We actually saw a 14, and that has a 0.003 probability. That's a very small probability. Does that make sense? So probabilities are numbers between 0 and 1, so numbers close to 0 are very unlikely, right? So statisticians use this number, the p-value, for making hypothesis test decisions. And we can make decisions on, for example, the slope of a regression line. Is this equal to 0 or not? What would a slope of 0 look like? When you have a line, what does the slope of 0? It's horizontal. And if the line is horizontal, that means that the x value has no control over the y value. In other words, there's no relationship between those two. So we might be interested in whether the slope is 0 or not, right? And if we do that, we end up with a hypothesis test and a p-value. In fact, one of these that I decided not to show you, but here I am showing you anyway. This is the output for a linear regression between, it was the amount of lactic acid in a cheddar cheese sample and the taste of the cheddar cheese. And it had, the taste was negative 29 plus 38 times the amount of lactic acid. So that's the formula. But is that slope 0? Over here you see a p-value. And that p-value is really small. And the small p-value is evidence that the null model is not true. In this case, the null model would be that the slope is 0. In the baby case, it would be that the babies don't have a preference. So the fact that we got a small p-value is evidence against that. And therefore, we end up deciding that they do have a preference. Does that make sense? And it's 12 o'clock. I did it. So I was trying very hard to close at 12 o'clock. Are there any questions?
I have a question. What made you become a statistician? I think a lot of times kids think of math and don't, and think of it
Unfortunately,
truly
I don't
math.
have a really good answer for that
That's
because I
okay.
kind of drifted into it.
That is an answer then, yeah.
So in college, I was a math and computer science major, and I had an internship in computer science between my junior and senior year. And I chose to never be in computer science again after my internship. So I decided I'd be a mathematician, and I went to graduate school for math. And then I chose to major in probability for math, basically because my advisor was a nice guy and I wanted to work with him. I mean, I really wish I made my decisions in life a little bit more thought out way, but that's the truth. He was a nice guy and he knew how to teach, and so I ended up doing what he did.
You're not the only one who chooses such things.
Yeah, that's probably common. Yeah.
And then when you are a major in probability and you are looking for jobs, you tell everybody you're a statistician because there are a lot more jobs in statistics than there are in probability. So I would encourage you to look at the MT-StatPal site because it's designed to help our teachers teach the introductory statistics class on campus. And so there are a lot of lessons there that could be modified to teach the lower grades.
Thank you.
Yeah, thank you.